Before going into the different tamper methods, it is important to understand how smart electricity meter works and how it is connected. The picture on the left shows how a single-phase electricity meter is connected. In the drawing, the red arrow connected to the first terminal on the left corresponds to line in, the red arrow connected to the second terminal on the left corresponds to line out, the black arrow connected to the third terminal on the left corresponds to neutral in, and the black arrow connected to the fourth terminal on the left corresponds to neutral out. In this configuration, the energy consumption is calculated by measuring the voltage between line in and neutral in and the current sensed across a shunt connected between line in and line out. The sum of the voltage current product is used to calculate the active power. This is also equivalent to the product of the RMS voltage and RMS current multiplied by the cosine of the angle between the voltage and current. The figure on the right shows a three-phase meter. This is similar to three one-phase meters with the voltage being measured between a particular phase's line and the neutral, and the current being measured between the corresponding phase's line in and line out terminals. To calculate the total active power for a three-phase meter, the active power of each individual phase is added together. By accumulating the active power, you calculate the active energy, which is the quantity that utility customers are billed by. Now that we went over the meter connections, let's talk about some common tampering methods. One of these common tampering methods is to reverse the connections on a meter. On the picture on the left, the line in and line out wires have been swapped. When swapping the wires, there is a risk to the tamperer because of the potentially harmful mains voltage that could shock the tamperer. The swap line connections actually cause a negative value for active power. Once this value is accumulated, it subtracts from the total accumulated energy consumption readings, thereby reducing what customers will be charged. For the one-phase scenario, care has to be taken, though, to make sure that the reverse connections have not been left in place long enough for the total accumulated energy consumption readings to read a negative value, which would be a red flag for utilities if a customer consumes and does not produce any electricity. For a three-phase system, one possible reverse connection configuration is to only swap the line in and line out wires for one phase. For a balanced load on each phase, this would cause a total energy consumption of 1/3 of the correct energy consumption because the negative readings from the swap phase would cancel out the positive readings of another phase. For helping detect this form of tampering, the sign of the active power should be monitored since it may indicate reverse connection tampering. A very common method to tamper with a meter is to place a metal object between a particular phase's line in and line out terminals as shown by the green arrows in the pictures. This metal forms a current divider with the current sensing circuitry, which leads to the metal object bypassing current so that the sensing circuitry senses less current than what is actually consumed, thereby reducing the active power readings and total cumulative energy readings. In addition, there is a risk to the tamperer because of the potentially harmful mains voltage when the tamperer tries to connect the metal, as well as afterwards if the metal is exposed. To deal with unbalanced current tampering, the terminal block cover is the first line of defense. In addition, you could also measure the neutral current. In a one-phase application, the neutral current should be equal to the line current. If there's a large mismatch between these readings, it could indicate tampering. In addition, for the one-phase scenario, metrology calculations can still be accurately calculated by using the current readings from the neutral channel. Additionally, disconnecting a lead is one way a meter may be tampered. Limp or live-only mode allows the meter to function in a limited way with one lead completely disconnected. For this configuration, a parasitic CT can be used to extract the load power from the current flowing in the remaining connected lead for high current loads. This would work regardless of which lead is disconnected. Alternatively, a backup battery could be used to power the meter for this scenario. For metrology readings, since no voltage is available, the measured current is multiplied by the meter's nominal voltage to produce the measured power. One of the most common ways someone tries to tamper with a meter is to apply a magnet on it. This magnet affects transformers and power supplies, as well as current transformer current sensors. This video shows how a magnet could affect a ferrite core transformer in a power supply. To demonstrate how a magnet could affect the ferrite core transformer in a power supply, we measured the output voltage of the power supply. Here we see that it is 3.391 volts when each phase has 230 volts applied to it. Now we'll see what the reading is when we apply a powerful magnet to the power supply transformer. For this test, for safety reasons, we place a physically smaller magnet than one used for e-meters, but we place it closer to the transformer in order to better simulate the actual conditions of when someone performs magnetic tampering. Here we place the magnet on top of the ferrite core transformer. So we close the system up and apply the same 230 volts input from our source generator. If we look at the output voltage of the power supply, we see that it doesn't go up to 3.391 volts. In fact, it doesn't go above 0.1 volts, as you'd expect. And this is because of the effect of the magnet on the power supply transformer. To deal with magnetic tamper attacks, power supply transformers that are either magnetically immune or sufficiently magnetically resistant are used so that they could withstand these attacks. In systems that do not require a power supply transformer with a large drive, it is common to also see a cap drop transformerless supply used instead, since they are magnetically immune. Strong magnets can also affect current transformer current sensors. This video shows the effect of magnets on current transformers. To show the effect of magnetic tampering, we apply 230 volts, 5 amps, and unity power factor on each phase of electricity meter. To show the effects of tampering, we use a PC GUI that will display the active power readings of each phase. Here we see that approximately 1150 watts has been applied to each individual phase. Now we'll see how some of these values would change when we apply a magnet on particular CT. For this test, we applied the magnet on top of the CT for phase C. After applying the magnet, we then applied the same 230 volts 5 amp unity power factor conditions. Here we see that the active power readings have decreased for phase C from 1150 watts down to 43 watts. As a result, the consumer will be charged much less electricity than what is actually being used. That is all because of the effect of the magnet on the current transformer current sensor. In the video, a physically small size magnet is used to show the effect of magnets on CTs. It should be noted that larger magnets cause a larger drop in readings. A strong enough magnet could even cause a zero current reading from a CT. In addition, multiple CTs could be affected by the same magnet, with the closest CT most affected by the magnet. One method to deal with the effect of magnets on CTs is to try to shield the magnet. However, CTs can only be shielded to a certain point. Due to this, shunt sensors are typically used for systems that should be magnetically immune. In addition, it is also common to detect strong magnetic fields and take special actions when a strong magnetic field is detected.